So the first few problems on the worksheet were, bless you, about weight and density. So number 1 is asking us find the weight of a 12-foot long piece of 3/4 inch diameter round brass. So we have our table on page 147 of your industrial mechanics book. Brass 3/4 inch is 1.63, and that is pounds per foot. And so to find the weight of that, we take the length, 12 feet, times that number. What does that give us, 19.56 pounds? Any questions on that one? So number 2, we're at a 16-foot piece of 1 inch square steel stock. So 1 inch square, is it 3.4? Again, that's pounds per foot. And we take that times the length of 16 feet times that gives us 54.4. Perfect. Number 3 is now venturing into steel sheets, or just sheets of material, I should say. So we have 6 sheets of 4 foot by 8 foot, 5/8 thick. And so we find our 5/8 steel. What is that, 25.5? Now this is pounds per square foot. So we have to take our square footage per sheet, a 4x8 sheet. How do we find the square footage? Yeah, 4 times 8, length times width. 4 times 8 is 32 square feet. So that is just 32 square feet times the 25.5 times 6 sheets. Perfect. What's that come out to be? 4,896 pounds. Are you guys used to using LB for pounds, or are you guys used to using the hashtag for pounds? Or kind of either one? Okay. When I'm doing straight math, I usually use LB, but when I'm doing some of the structural stuff, I use the hashtags. Be aware I'll probably switch back and forth as I go through here. Problem number 4. We have 12 sheets of 2 foot by 4 foot steel at 1 1/4 inch thick. So 1 1/4, what do we get there? 51. Again, that is pounds per square foot. What's the area per sheet? 2 times 4 is 8. So 8 square feet. Then, of course, times 12 sheets. Yep. Also 48.96, yes. I couldn't make that happen the same again if I tried. Any questions on those? So number 5, we're talking about the term that's used in your textbook is a cylindrical vessel, or just a vessel. See if I can actually spell this right on the first time. I think that's close. Cylindrical vessel. To find the surface area, and the vessel we have here is 4 foot diameter by 8 foot tall. So there's 2 pieces to this. We have the area of the bottom, which is just a circle. How do we find the area of a circle? Pi times radius squared. So here that'll be 3.14 for pi. What's our radius? 2. We have a diameter of 4, so the radius is 2. So 2 feet squared times that is what, 12.56 square feet? So that's the area of the bottom. Then we need the area of the sides. Remember, the area of the sides, we called it a lateral area is the technical term for it. It is the circumference of the bottom times the height. So how do we find the circumference of a circle? Pi times diameter, and then, of course, to get the area, it'll be times that height. So 3.14 times 4 feet times 8 feet tall. You got it. And what does that come out to be? 100.48 square feet. So the total, if I add those up, what's that? 113.04. Any questions on that one? If you're struggling with those, I highly recommend just go ahead and draw out the picture. It sometimes helps. So number 6. Okay, so you use the pi button. I just use 3.14, just a round off difference. Yeah. On my answer key, if you're taking the quiz, I'll have both numbers, and anything in between them will be fine. Yes, when you use the pi button, it uses like 3.1415926. Yeah. So total weight. So really, it's a cylindrical vessel again. That is 5 feet in diameter by 7 feet high by a thickness of 1/4 inch steel. So the 1/4 inch steel, we'll need that later. If we look that up, what is that, 10.2 pounds? And that is, of course, pounds per square foot still. So before we can use that, we need the total area of this vessel. So the area of the bottom, 3.14 times what? So times the radius squared times 2.5 squared. So that's 6.25 times 3.14. What's that give us? 625. Perfect. Square feet. Then we need the area of the sides. That'll be pi times 3.14 times 5 times 7 times the diameter times the height. What does that give us? 109.9. Perfect. We add those together to get a total. 129.525 square feet. Then we'll multiply that by the 10.2 pounds per square foot. Giving us what? Okay. That's just, pounds. Yep. So if you rounded it 1,321.2, 0.16, however you rounded it would be fine. I would recommend at least one decimal place when you're rounding those off. Questions on that one? Okay. Number 7, bend ratio. Bending ratio, if we have a 7/16 inch rope and a 3.5 inch or 3.5 inch pulley, how do we find the bending ratio? You bet. Yeah, it's pulley divided by a rope. 3.5 divided by 7/16. What's that give us for bending ratio? So when you punch this in the calculator, you got to be careful. So you got 3.5 divided by, you got to put in parentheses, 7 divided by 16. I'm getting 8. If you just type in 3.5 divided by 7 divided by 16, it actually ends up dividing it twice. So yeah, for those that didn't catch that, notice I put the 7/16 in parentheses when I divided. So number 8. Find the bending efficiency of a 3/4 inch rope over a 6-inch pulley. So first we need to find what? Yeah, bending ratio using the pulley diameter, 6 inches divided by 3/4 inch rope. What does that give us? 8 is our bending ratio. Then we look at our table. Yep, you find 8, you trace that up, and looks like it's pretty much right exactly at 85. Yep. So 85%, or if you list it as 0.85, either one would be your bending efficiency there. Anybody have any questions on using that little graph? I realize it is kind of a guess. So again, on a quiz, I'll probably have a 2% above or below. If you're anywhere from 83 to 87 would have been acceptable there. Number 9. So find the rated load. After bending for a 3/8 inch rope on a 6-inch pulley when the rope is rated for 2,380 pounds. So we just got to go back through the whole process. We start with the bending ratio. Bending ratio will be found doing what? 6 divided by 3/8, which is going to give us 16. Then we look at the chart. 16 changes up to 90. Perfect. So then to find the rating, we take the rope rating, 2,380 pounds, times 0.90 for the 90%, giving us 2142. Perfect. Any questions there?
You also take that.
Yeah. Yep. Yeah. 2%. Yeah. So you were like 2120 or something like that. Yeah. Yeah, I'd be up or down by 2% again. Realistically, in practice, the engineer in me says you'd want to underestimate it. So you'd want to get it to 88 or 89% so that your rating is going to be lower than what the rope can actually hold. No, it's just below 90. Yeah. Number 10, find the working load limit. For a 3/4 inch diameter fiber core rope, if you looked at it in the chart, it's got a breaking strength, 46,400 pounds. That's page 157 if you're trying to look it up. If a safety factor of 4 is used. Exactly. Working load limit is the ultimate strength. I can't remember what they call it on the table. They call it breaking strength. Material engineering, the term is ultimate strength is when the material breaks. It's the ultimate strength, 46,400 pounds, divided by whatever your safety factor is. So what do you get there? 11,600? Perfect. Number 11. We're going to find the required breaking strength. So that's what the rope needs to be rated at. If it needs to support 7,300 pounds, and with a safety factor of 6. So we're going backwards now. We're starting with what we actually need to hold, which is typically what you would do. 7,300 pounds times that safety factor of 6, which will give us 43,800 pounds. So if you wanted to look in the table in the book, what is this, 157? I didn't ask you to do this next part, but yeah, 157, they've got your rated ropes there. I didn't really say what kind of rope. I didn't say fiber core or anything else like that. But to have a minimum of 43,000, if you're looking at a steel fiber core, looks like 3/4 inch is your minimum diameter. Any questions so far? Number 12. So percent elongation. It was 60 inches new and is now 60.3 inches. So for percent elongation, we first find the elongation. How do we find that? Yeah, the used length minus the new length. Then we're going to divide that by the new length, 60. So if we divide that, and of course that's going to be times the 100%. So 60.3 divided, come on, there we go. So 60.3 minus 60. Now it's important that you either put that in parentheses, or what I usually do is just hit enter or equals before you divide. If you divide before you hit equals, your order of operations gets all messed up. So you've got the 0.3 inches of elongation, then divide by 60. So at the 0.005 times 100 to turn it into a percent, you get 0.5%. Usually, I think industrial standard in most industries is 1.5% maximum elongation before you scrap a chain. So 13, find the maximum allowable worn length for a chain. If it's 180 inches new, and you're allowed 1.5%. So what this means is we actually just we're adding 1.5% to the original length. The original length is 100%. We're adding 1.5%, which means the worn length can be 101.5%. Does everybody see where the 101.5 came from? Just 100 adding that percent of allowable elongation. So then we take the new length, 180 inches, times, what's that? Perfect. We turn 101.5% into a decimal, just move the decimal over 2 spots, 1.015. And that calculates out to be 182.7 inches. Now, if you're not using something that can measure in decimal inches, again, this is not something that will be on the quiz, but just something I wanted to show you. If you're measuring this out with a tape measure where you're probably measuring to the nearest 16th or maybe a 32nd of an inch, what you can do is you take the 182 and we take the 0.7 inches. If I want to turn that into, let's say, a 32nd, just to be a little more precise, I just put the 0.7, the decimal portion of the inches, over 1, and I want the denominator to be 32. So I do 1 times 32 is 32. If I multiply the bottom of a fraction, I have to multiply the top of a fraction. 0.7 times 32 is 22.4. So what this is saying is this is between 22 and 23 30-seconds. Slightly closer to 22, it's 22.4. That reduces to 11/16. So if I'm measuring that chain, when the overall length is 182 and 11/16 inches, it is time to get rid of it. Now, like I said, we typically will measure shorter sections rather than the full 15 feet of a chain, just because you can have localized wear. Okay. Any questions on 1 through 13 at all?
Well, you guys just rounded up on 12, right?
12, actually that came out exactly. So the 60.3 minus 60 is 0.3.
Yep.
Then 0.3 divided by 60 is 0.005. You look confused yet?
Yeah, I did something wrong. I did 0.3 divided by 60.
Oh, you did 60.3 on bottom. It's always the new length that goes on bottom. So this is always got to be the new length. Yeah, that will change it just slightly. Okay, so 14 through 16 are just finding missing angles. So if we have 51 degrees, 79 degrees, what's this one have to be? 50. Again, it's just 180. We subtract the other two angles to get what's left over. And this one, if this angle is 131, this angle has to be 49. Again, a straight line is 180 degrees. So it's just 180 minus 131 to get the 49. Oops. So this is an example we didn't really go over. This is 104 degrees here. These little hash marks means those two sides are equal. One rule in triangles is that the longest side has to be opposite the largest angle, and the smallest side has to be opposite the smallest angle. A consequence of that is if these two sides are the same, what does it say about those two angles? They're the same. They're equal. So we take 180 minus the 104, gives us 76 degrees, divide by 2, that is split between those angles. So they're each 38. In a right triangle, if we know that's 68 degrees, we know this is 90 degrees. A shortcut is we know that 180 minus 90 is 90. So we can just start with 90 minus 68 to get 22 degrees. Good. My pen's lagging today. So here, if this angle is 111 degrees, so this is 69, which means this one is 21. Perfect. Any questions on number 14? So number 15 are these right triangles. So I have 6, 8, and 10. How do we tell? You got a squared plus b squared equals c squared. And we know that c has to be the longest side. So if this is a right triangle, 10 would have to be the hypotenuse. So a and b would be the 6 and the 8. So 6 squared plus 8 squared, does that equal 10 squared? Yes. 36 plus 64 is 100, and that is 10 squared. How about 5 inches, 12 inches, and 13 inches? 14, sorry. 13 would have made it a right triangle. So if we try that out, it would be 5 squared plus 12 squared We're not sure if it equals 14 squared. 5 squared is 25. 12 squared is 144. That adds up to 169. 14 squared is 196. So that is a no for that one. And part C, I suppose I shouldn't put the right angle in there. 7, 24, and 25. So it'd be 7 squared plus 24 squared. And again, does that equal 25 squared? Yeah, I know. I gave it away when I put that in. 49 plus 576 is 625. That is 25 squared. Any questions on that one? Okay. So number 16, trying to find missing sides. So we got 12 and 16. We need to decide, is that missing side a leg or the hypotenuse? It's hypotenuse, so I'll make it C. So it's 12 squared plus 16 squared equals C squared. So 12 squared, 144, 16 squared, 256, added together, 400, and then to find C, square root, which is 20. So that hypotenuse is 20 inches. If I'm just entering this in the calculator, what I enter is going to look something like this. I do my square root symbol first, depending on the brand of calculator you're using. Most of them you do the square root first. Then I just do 12 squared plus 16 squared. Close the parentheses for the square root. I hit equals and it spits out the 20. If your calculator functions differently than that, let me know and I'll help you figure it out as we get started on the quiz. Part B. I gave this one away in the last problem too. 512, are we looking for the hypotenuse or the one of the legs? Hypotenuse, that's C. So A and B are the 5 and 12, so 5 squared plus 12 squared equals C squared. 5 squared is 25. 12 squared, 144. That adds up to 169. And of course, to find C, square root to get 13. Part C is the only one where we had to find a leg. So I'm going to call that A, since it's the leg, or one of the legs. 48 and 50. So I have A squared plus, what goes next? 48 squared. Equals 50 squared. So 48 squared is 2304. 50 squared, 2500. Then we would solve that by subtracting the 2304, giving us that A squared is 196. And then square root to get A is 14. Now again, if I'm just punching this in the calculator, I'm not going to write it out like that. I am going to do the square root of the hypotenuse squared, so 50 squared, minus the known leg, which is 48 squared. Then close my parentheses, giving me the 14. Any questions on anything on the worksheet? Or anybody worried about anything on the quiz?
Yeah, I feel like I took your notes down. You realize because I had that for back to number 12.
Yep.
I had as your equation change in length over the.
Yeah, the new length would be the purchased new, not the after that's worn. Not as like new as in recent. Yeah.
Right.
So you were using the worn length. The 60.3 was the worn length. Got it. There we go. So what we want to talk about is center of mass. And we're just going to talk about it in a one-dimensional sense here as being strung across a single beam. Oops, thank you. And so to start off with, let's look at what we call a uniform load. And a uniform load is probably the most common. It's just like a steel bar or a beam that is the same all the way through its length. So it's the same weight per linear foot at everywhere along its length. And the way we typically represent a uniform load is just with a rectangle. And we might say that that is 12 pounds per foot. So it's pounds per linear foot. Each linear foot of that is 12 pounds. And if the length is 16 feet. For a uniform load like that, the center of mass is always at the mid-span. So for this one, center of mass is 8 feet from either end. Now, when we're engineering, we tend to work from the left end of any sort of beam or saddle like this. Just because you go left to right, we tend to work left to right. So if I were to say that the center of mass is at 8 feet, I'm saying it is 8 feet from the left end of that structure. The other thing we need to know is total mass. And this is something we kind of looked at last time around. The total mass was that pounds per foot times the length. So 16 feet times 12 pounds per foot, which in this case, 192 total pounds. So for a uniform mass, kind of boring. Just find the total mass, it's right in the center. What if it's not a uniform mass? So let's look at if we have some sort of a beam, and we're going to do a physics beam here. It's a weightless beam with what we call concentrated loads. The old vernacular is a point load. It's a load that occurs at a single point. So let's say that we go 6 feet from this end of the beam. We have a 2,000 pound load. And that is 10 feet from this end of the beam. The center of mass for concentrated loads is the average distance. I should be careful here. The location of the center of mass for multiple concentrated loads is the average distance from the left end. For a single concentrated load, the center of mass is just where that load is. So this mass right here is 2,000 pounds at 6 feet, and that's it. There is only one load there. So the calculation would come if we're combining more than one concentrated load. Let's say 4 feet from this end, we have 800 pounds. We go another 8 feet. And 6 feet from this end, we have, let's just go with 1,000 pounds. So to find the center of mass, the location of the center of mass here, we have to find the average distance from the left end. Total weight, of course, would be what? 1,800. There we go. Just the 800 plus the 1,000. The location, then, we find the average distance. So this one is 800 pounds at 4 feet. So we do 800 times 4. It's 3,200. And that unit is foot-pounds. Or pound-feet, I believe some of your textbooks use. The second one is 1,000 pounds at what distance? Careful. 12 feet. So that is 12,000 pounds, or 12,000 foot-pounds. We add those together, we got 15,200 foot-pounds of total load. Now, this is actually a moment. It's a rotation about, since we were going from this end, it's about this end of that structure. To find the distance to the center of mass, or the average location, then, we take that 15,200 foot-pounds, and we want a location. We want feet, so we divide it by the total pounds. 1,800 pounds. So 15,200, come here, divided by 1,800 would give us 8.44 feet. So the location of that center of mass is right here at 8.44 feet from the left end. So the center of mass would be the 1,800 pounds at 8.44 feet from the left end.
That last 6 feet doesn't even matter in this equation, right?
Nope. It's just because that'll be the total length then would be 18 feet. At some point, we're going to come back and we're going to find what's called the reactions. That's how much it takes if we're putting this in a sling to hold up each end. And then that link will come into play there. But yeah. So what is the importance? Yes, sir. Oh, sorry. Oh, sure. Let me get that out of there. Is that better? Okay. I'll try not to highlight. I forgot about that. I know you told me that last time. The significance of the center of mass is we can treat this whole beam, instead of all of this, we can treat it as a single beam that has one 1,800-pound load at that location at 8.44 feet from the left end of the beam, or whatever the structure is. When we come back later to try to find how much it's going to hold, what's the load at each end, then when you put it in a sling or on a support, that comes into play. Then we can use it as that single load. So looking at your worksheet there, number 1, you have 4 feet to an 800-pound load, an additional 5 feet to an 1,100-pound load, and 6 feet to the end. What is my total load?
1,900.
1,900. Perfect. So now I need to find my average distance to that for my center of mass. So I start with the 800-pound load times what? Times 4. So 3,200. Then what?
1,100 times 13.
Times 9. There we go. 1,100 at 9 feet. So it's 9,900. So we add that up to get 13,100 foot-pounds is that total moment or rotation. Then we just divide that by the 1,900 pounds of total weight, giving us 6.89, there goes 6.895 feet. So again, what that means is we could treat that beam as though it has a single 1,900-pound load at 6.895 feet from the left end. But what if we have multiple distributed loads, uniform loads? This would be like number 3. So for 10 feet, we have 9.2 pounds per linear foot. Then for the last 6 feet, we have 16.9 pounds per linear foot. If you hear me use the phrase PLF, that's pounds per linear foot. So what we need to do is we're going to turn these uniform loads into single concentrated loads. So what that means is this load here becomes a single load 5 feet from the end. Remember, it's at the middle of the uniform load, and it's 9.2 pounds per foot times 10 feet, giving us 92 pounds. So everybody see where I got the 92 pounds and the 5 feet there? Any questions on it? You look lost back there. Okay. So since this is a 10-foot distributed load, the location is just at the center of the 10 feet. So that's where the 5 feet comes from. Then the total load, the total load is just kind of what we were doing in the last time. It's the 9.2 pounds per foot times that total length of 10 feet. Gives us a total of 92 pounds. So what's happening is now that distributed load is just a 92-pound concentrated load 5 feet from this end. Now we have to do the same for the other load. That concentrated load would be half of 6 would be 3 feet. But now coming from this all the way from this end, what would that distance be? 13. Good. The 10 plus the 3. And then we find the total load there is going to be the 16.9 pounds per foot times that total length was, careful, 6 feet for the load. Yep. The location's at 13 feet, but it's 6 feet from the load. So 6 times 16.9 is what, 101.4 or something like that? 101.4 pounds. Bless you. So this is 101.4 pounds. It is 13 feet all the way from the left end to that load. Or I could have just put in 8 feet here. I could have subtracted the 5 and say it's 8 feet between them. The 13 feet is going to be what we need, though, to find the center of mass. So we've turned the uniform loads, the distributed loads, into concentrated loads. Now we can find the center of mass. The center of mass is always found using, these are what they call equivalent concentrated loads. So now to find the center of mass, what is the total load? Yep, 101.4 plus 92. So 193.4 pounds. So now we need to find the total moment, so we can find our average distance. So it's always distance from left end times the load. So for the first one here, it is 5 feet from the left end times the load of 92 pounds, giving us 460 foot-pounds. For the second piece here, that's 13 feet to that second load times 101.4 pounds. And that one I'll have to put on the calculator. That sounds right, 1318.2, yep. Foot-pounds. We add those together. Perfect, 1778.2 foot-pounds. And then what do? Divide by the total of 193.4 pounds. What does that give us for feet? So 1.190 feet. So the center of mass here, the centroid we call it, is 193.4 pounds at 9.190 feet. And again, that is from the left end. So this is equivalent to saying we have 193.4 pound weight, 9.190 feet from the left end of that structure. It's possible to have more than 2. Let's look at number 6. Does everybody have that one down, or need a second for me to let you catch up? Okay. Well, it's because of that extra set of steps. So your first step is always to convert distributed loads to concentrated loads. And then from there you find the average distance from the left end. So number 6 is going to take a few minutes. So number 6 has 3 sections. We've got a 4-foot section that's 9.8 pounds per linear foot. Then a 3-foot section that's 17.4 PLF. And then a 7-foot section that's 9.8 pounds per linear foot. So now remember, we're going to convert these to equivalent concentrated loads. So the first one's going to be at the center of this. How far is that going to be from the left end? 2 feet in the middle, half of the 4. Perfect. The next one will be here. How far is that going to be from the left end? There you go. Half of 3 is 1.5 plus the 4. Makes that 5.5 feet from the left end. Then the next one will be here. What's that location from the left end? Yes. Half of 7 is 3.5, 3.5. 4 plus 3 is 7, plus 3.5 is 10.5, 10.5 feet. To find the size of each of those, how are we going to find the size of this one? 4 feet times 9.8 pounds per foot. What is that? 39.2? So it's 39.2 pounds. How about this one here? Three feet times 7.4 pounds per foot is 52.2 pounds. And this last one, how do we find that? 7 feet times 9.8 pounds per foot. Perfect. Which is, what, 68.6 pounds. Perfect. Now I'm going to pause there. Any questions on where this came from in the blue or in the circle there? So now our next step is going to be to find the center of mass. So we find the total load. We add those three up, we get what? $150 exactly, isn't it? Oh, nice. So 150 total pounds of load. What's our next step? Average 160. Yeah, that works. Yeah, next step is average distance from left end. So we take the load or the distance, it doesn't matter. For this first one, what are we going to multiply? For this one over here. Oh, we actually just did the load there is 39.2, and its distance from the left end is the 2 feet. So 39.2 times 2 or 2 times 39.2, either way, is what? 78.4. That is foot-pounds. The next one here, this is 52.2 pounds. What's its distance from the left end? 5.5. So 52.2 times, I'm going to rate it as 5.5 because that's what you're going to put in your calculator anyway. 287.1. Again, foot-pounds. And then the last one here, this one is 68.6 times what? Times 10.5. Giving us 722.4 foot-pounds. If we find that total, we got 1,087.9 foot-pounds. Then what do we do? That's where we divide by the total weight. 68.6 times 10.5. 720.3 it is, actually. So let me change that. They'll change our total here. So is that 0.8, 15, 1,085.8. Does that look better for a total? So then we take the 1,085.8 divided by our total weight of 160 to get a distance of 6.786. So what that is telling us is that this whole structure can be reduced to a single concentrated load of 160 pounds at a distance of 6.786 feet from the left end. Now at number 7 on your worksheet is a triangular load. I'm just going to show you this part quick, and that's going to be it. To find the centroid of a triangular load there, that's 12 feet. It goes from 14.2 pounds per foot down to 0 pounds per foot. So this would be if you have a tapered piece of stock. So obviously going to be heavier at the thick end, lighter at the thin end. The centroid for a triangular load is 1/3 of the distance from the larger side. So 1/3 of 12 would be 4 feet. And then the location of that centroid, or the amount, is the total load. It's just the area of a triangle. So it's that 14.2 pounds per foot times the 12 feet, but then it's a triangle, so we have to divide it by 2. I believe that comes out to 86.2 total pounds. So the centroid for that triangular load, it's equivalent to being 86.2 pounds, concentrated load 4 feet from the left end. Why do we care about the centroids? I mentioned it helps us find the load at each end when we're trying to support this. If you have a beam, whether it's being supported from below, like in a house beam, a structural beam, or whether it's being supported from above, like in a sling, which is probably more like what you're going to do. You're going to have tracks in the above or cranes, and you're going to be supporting stuff. These ends are what we refer to as reaction loads. It helps when I put my C in there. They're called a reaction load because it reacts to the load that's on the beam or the structure. Like here, if this were a box, let's say this is 10 feet, and let's say this weighs, or a beam or whatever that weighs 12 pounds per foot. The total load there would be 12 times 10, 120 pounds, right? Since this is uniform, the center of mass would be right in the middle. So that means each end, each of these ropes or cables supporting each end would have to hold half of it. They would be holding 60 pounds. It's not that they're not capable of holding more. It's that that's all they're required to take. The load they hold is a reaction to the load on the beam it's supporting. That's where the term reaction load comes from. So because this was, the center of mass was at the center here, half the load went to each side. But if it's not at the center, the formula is similar to our center of mass formula. So let's say here we have a 10-foot beam, again supported in a sling, but now our center of mass, we got 4 feet from this end, we have a 1,000 pound load. Now, if I call this the left end and the right end, which end is going to take more of the load here? The left, the end that's closer to the load. So we know that the left reaction better be bigger than the right reaction. But the way we find it, let's find the right side. It is the total load times the distance to the left. DL stands for distance to the left. And that is the distance to the left end of the beam. Then that is going to be divided by the total length of the beam. So again, this is for the right side. So here we have the total load of 1,000 pounds times, what's the distance to the left end from that load? 4 feet, divided by the total length of the beam, 10 feet. So it's 4,000 divided by 10, or 400 pounds. So the right end here has to hold 400 pounds. The left end has to hold 6. They have to add up. But let's do a formula to make sure. So the left side it's just total load times distance to the right end, that dr is distance to the right end, divided by the length. So here that will be total load of 1,000 pounds. The distance to the right end, then we have to do a little subtraction. 10 minus 4 makes that 6 feet. Divided by the total length of 10. And it does come out to 600 pounds. So the key is, once we have the center of mass, to find the load on the right end, it's the distance from the center of mass to the opposite end that matters. So for the load on the right side, it was the total load times the distance to the left, the other end, then divided by the total length. So if I have it's a little disinteresting. Let me make this a little more interesting than that. So let's say we have a 16-foot beam here. And at 6 feet from the left end, we have 2,500 pounds. So I want to find my left end reaction and my right end reaction. It doesn't matter which one you find first. I was always trained as an engineer, you hold the left end fixed, and that means you find the right end first. It's just force of habit that I always find the right end first. So the right end, what are we going to use here? 2,500 is the total load times what distance do we use? 6 feet, the distance to the opposite end, the left end, divided by 16. So 2,500, my calculator will come up, there we go, times 6 divided by 16. 937.5. Now, if you were in a hurry, you could just subtract 2,500 minus the 937.5 to get the other end. But I like to double check. So let's do the left end. That'll be the total load of 2,500 times what distance? It's 10 feet to the opposite end, divided by 16. And that does come out to be 1,562.5 pounds. And so you double check them by adding those two up to make sure they add up to your total of 2,500 pounds. When we do a sling, we do not like to run the supporting cables or ropes straight up. Can I think of a reason why we don't like to do that? It sways. Any sort of pressure or variation in speed, this is going to start going back and forth. To stop that, even a slight angle on the cables will cause it to stabilize. Remember we mentioned 2 weeks ago that triangles are a rigid structure. By angling those cables in, What it really is, if we extended these up, that becomes a triangle. And so even though those are loose cables, for it to sway, one of the cables has to go slack. It can't just sway on tight cables very much. So this makes it a much more stable structure. The problem is, when you angle those cables in, it increases the amount of stress or weight on each cable, because the cable still needs to lift the total reaction load on each end, but then part of the force on the cable comes from the fact that it's pulling in as well. So if I have a structure here that requires, let's say it requires 1,200 pounds on this end and 1,600 pounds on that end, on the right ends. That would be if the cables are straight up. But if I am going to angle this cable here, and let's say this angle is 70 degrees, that cable has to be able to hold more than 1,200 pounds. The stress on the cable is going to increase because the cable is also pulling in as well as having to lift up for the 1,200 pounds. So there is something called a reduction factor. If you look, I believe there's a table in both books for this. Find the right page for the table. It's 151 in the big book, the one I'm looking for. It is. In your big book, it's page 151. In the little book, I had this one marked, I thought. I'm not seeing it right now in the little book, but in the big book is page, what's that? That could be it. I could have just flipped right by it. That's the start of it, but it doesn't have the table there. So anyway, in the big book, there's page 153. And so you see there's angles from the horizontal. That's just the angle to the beam that you're supporting. And then there's a loss factor. If you look at for 70, it shows a loss factor of 0.94 for 70 degrees. Yes, yeah, that's my reduction factor, loss factor. Where that comes from, because this table, you see, it goes every 5 degrees from 30 up to 90, and you could always just estimate it. If you go to the next smaller angle, it's going to give you a safety margin. But where that actually comes from is that is simply the sine of 70 degrees, a little bit of basic trig. So if I pull up on my calculator, hopefully I'm set in degree mode here. I press the sine key of 70 degrees, hit equals, and see I get 0.93969, which is 0.940. That's where that 0.940 comes from. So what I have to do to figure out what that cable is needed, or what needs to hold. So my needed tension on the cable is to take the required reaction, which is the 1,200 pounds, divided by the 0.940. So 1,200 pounds divided by 0.940 tells us 1,276.6 pounds. So that cable, in order to support the 1,200 pound reaction, the cable is actually going to have a stress of 1,276.6 pounds on it. The smaller the angle to the horizontal, so if it's perfectly vertical, the angle to the horizontal is going to be 90 degrees, yes. So the smaller the angle to the horizontal, the greater that reduction is going to be. So let's say this is at 50 degrees here. You could look up in the table, 50 degrees is 0.766. So that one is 1,600 pounds. So the needed tension on that cable is 1,600 divided by 0.766. Or 2,088.8. So that cable has to hold 2,088.8 pounds in order to support that 1,600 pound reaction. The other way this gets used is to look at a cable rating or a rope rating. Let's say your cable is rated for 3,000 pounds. But it's going to be sitting at a 60-degree angle. So here's my beam. It's going to sit at a 60-degree angle here. It's rated at 3,000 pounds. What is the actual reaction it can support? Well, now we take the rated load times that loss factor. So for 60, the loss factor is 0.866, I believe. So it's the 3,000 pounds rated load for the cable times 0.866. It's going to be 25 something. 25.98. So that 3,000 pound cable, if it's at a 60-degree angle, is only going to be capable of supporting 2,598 pounds of a reaction. Now I realize I just fit like 2 weeks of a structural design course into 28 minutes. 48 minutes, but I don't expect you to have absorbed all of that. The worksheet is there for you to practice. We did not get to any sort of pulley reduction mechanical advantage with pulleys. That's actually a fairly simple one that you'll get to with Bob when you go over it. Again, I'm not collecting this worksheet, so the worksheet is yours to practice whatever if you want. If you are interested in finding answers to it, send me an email. Those of you that don't have my email, it is todd.hoff@northwoodtech.edu. And I can send you the solutions to that worksheet if you want them. I will get your quizzes graded, and I'll try to get them back to Bob, so he'll get them back to you sometime in the next couple of sessions that you guys have. So with that, you guys